Welcome to Lecture 15 for Chemistry 312 Radiochemistry. This lecture is on the chemistry of americium and curium, and it's in two parts. The readings for the lecture on americium and curium can be found in the chapters on americium and curium in the chemistry of the actinides and transactinides. The links for both these chapters are available on the Canvas site. These lectures are combined, the chemistry of americium and curium, because the elements have some pretty strong chemical similarities. Within these lectures, we're going to cover americium, then go on and explore curium. The first part of the lectures will cover the nuclear properties, the production of isotopes, and the separation and purification of americium. Part 2 will then explore metallic states, compounds, solution chemistry, and coordination chemistry of americium, then go on to cover curium. And fundamentally in part 2, we'll just be highlighting some of the differences between curium and americium. The figures here show some examples of americium and curium. The silver button, that's some americium metal, whereas the glowing figure, that's actually from a shorter-lived curium-244 compound. And the glow is due to the short-lived isotope and the radiation effects, so the emission of the light due to heat from the decay. Let's start by reviewing some isotopes of americium. Americium, as we discussed in the very first chapter, can be made from a plutonium target. For numerous cases, the reactors used neutron capture of plutonium-239 to plutonium-240, 241, to 241 beta decays up to americium-241. Then there's consecutive capture on those isotopes. The main isotopes that are used for the chemistry of americium are the 241 and the 243. They're relatively long-lived, as one can explore on the table that's shown here. The half-life of the 241 being 432 years, the half-life of the 243 being 7,380 years. There are some uses for americium. Americium-241 is used in smoke detectors. This is due to the alpha decay. The alpha emission from the americium-241 provides a constant source of ionization within the smoke detector. This is due to the interaction of the alpha particle with air. When smoke enters the detector, this ionization decreases because the alpha particle will interact with smoke particles, which do not ionize as readily as air. This decrease is detected within the smoke detector, and that initiates the alarm. The americium-241 is also used as a neutron source. One can plate beryllium with americium. The alpha decay from the americium has a nuclear reaction with beryllium that liberates a neutron. So this is a source that can be used, a portable neutron source. The alpha decay can also be used for thickness gauging and material density. Americium-241 can also be used as a target for the production of curium-242 through the thermal neutron capture of americium-241. The isotope americium-243, longer lived isotope than the 241, preferable for studying the chemistry, can be produced by the irradiation of plutonium-242, and then that subsequent plutonium-243 undergoes beta decay, creating americium-243. One of the isotopes of americium, the 242, as shown here, has very large cross sections. Both the 242M and the 242 have fission cross sections which are above 1,000 barns. The 242 americium can actually achieve a critical mass with just 23 grams in a 5 gram per liter solution. Obviously, this would require the production of isotopically pure americium-243. A list of the isotopes shows that a large range of americium isotopes are available, as low as 232 and as high as 247. The decay routes tend to be alpha and beta minus with the heavier isotopes, then electron capture, and then some spontaneous fission isomer modes with the lighter routes. So some of these lighter isotopes are investigated to help explain some nuclear properties, particularly the spontaneous fission isomer. In solution, americium exhibits a number of different oxidation states. One can form stable from the 3 to the 6 oxidation states in solutions. The 3 and the 5 tend to be stable in dilute acids. The 5 and the 6 will form the dioxocations, the eel species, as we saw with plutonil, uranyl. So americium 2 is unstable. It's unlike some lanthanides, terbium, europium, samarium, which can form divalent oxidation states. The americium 2 has been observed from pulse radiolysis. There's an absorbance at 313 nanometers, and the oxidation state has a very short half-life. Americium 3 is the primary oxidation state one would find in solution. It's easy to prepare. One can dissolve metal in acid or dissolve the americium dioxide. Both will form the trivalent oxidation state. It's a pink solution in mineral acids. However, in higher concentrated perchloric solutions above 0.1 molar, americium can be yellow. There's an absorbance at 503 nanometers with a molar absorptivity of over 400. The transition band has been identified. The term symbols for the transitions from the ground state to the excited state for this absorbance are provided here. Term symbols describe the quantum mechanical states of the electrons. You may have seen term symbols in previous courses. There's also a link to a discussion on term symbols on the Canvas website. There are some shifts in this band position and the molar absorbance as a function of coordination, as shown here in the figure, where the free americium has this absorbance of 503 nanometers. And then as carbonate species are formed, you get a higher wavelength shift with the increase in coordination of the americium. For the free ion, they're on the order of 10 intersphere waters coordinating. Common property of the actinides have high coordination numbers. This value is based upon fluorescence studies that were used to determine the lifetime of the fluorescence with the quenching function of the coordination number of waters. Lifetime measurements were performed in H2O and D2O to determine these values. Americium 4 can be formed, but it requires complexation to stabilize this compound. One can dissolve the americium hydroxide in ammonia fluoride to stabilize the tetravalent oxidation state. Phosphate compounds can also be used to coordinate and stabilize americium 4. There's also routes where one can use carbonate solutions with oxidation to stabilize americium 4, and the absorbance spectra is provided here. And this is the absorbance of americium 4 in 13 molar ammonia fluoride. The absorbance data for pentavalent americium is shown here. This can be produced by the oxidation of americium 3 in near neutral solutions. Number of oxidizing agents, as shown here, ozone hyperchlorate peroxydisulfate can be used, or the reduction of americium 6 with bromide. You see that there are two peaks. Both of them are identified. Again, the term symbols are an identification of the electron configurations that are responsible for the transitions. And both these molar absorptivities are around 50. Americium 6, again, the other eel americium compound like americium 5. This can be produced by the oxidation of americium 3 with the peroxydisulfate or silver. Cerium 4 oxidizes the 4 to the 6, but not the 3 to the 6 completely. Carbonate and ozone or oxidation at 1.3 volts can also be used to produce and stabilize the americium-6 oxidation state. And the molar absorptivity is shown here, about 1,000 nanometers. And there's a smaller absorbance at 666 nanometers. Americium-7, shown here, being produced in very basic solutions under stringent conditions, including gamma radiation, high base. Americium-7 also has an absorbance near 740 nanometers. The thermodynamic data for the different americium oxidation states are shown here. This information can be used to both prepare and identify various americium oxidation states in solution. In addition to absorbance, americium-3 can also undergo luminescence, sometimes called phosphorescence. In this case, the americium is excited at the 503 nanometers. This excited electron state then can be converted to another state which has a lifetime. What's seen with americium is that there are two transitions shown here at 685 nanometers and 836 nanometers. One can measure the emission bands in the figure below. This is observed for the luminescence of americium-3 in acidic and carbonate media. So the absorbance is at the UV vis at a higher wavelength, lower energy. You get an emission. One can measure both the wavelength and the lifetime. For aqua ions, so for water, the lifetime of this band is on the order of 20 nanoseconds. So after the absorbance at 503 nanometers, the average lifetime of that excited state is 20 nanoseconds. This lifetime is extended with D2O, if one uses a deuterated water system, as opposed to a normal water system. That lifetime increases to over 150 nanoseconds. This is one of the routes for evaluating the coordination number of water around the metal center. For this case, it was performed with americium on luminescence. This is also done with lanthanide systems. And the emission and lifetime changes with speciation. So this fluorescence property is a tool for evaluating chemical forms. With water, the lifetime is 20 nanoseconds. With D2O, it's 155 nanoseconds. With the carbonate system, it's on the order of 35 nanoseconds. And the emission is slightly different for the carbonate system, where you have an emission close to 700 nanometers, versus with water, it's at 685 nanometers. So with a laser system, one can pulse a laser. The time in which the excitation occurs can be known, and then the lifetime measurement can be used through a detector system. This nanosecond lifetime is relatively short. With curium, we will show other fluorescence systems. Curium is more frequently measured for fluorescence than americium because the system is longer lifetime and more sensitive than the americium system. A factor that complicates the chemistry of americium is the radioactive decay itself. This can result in autoreduction and radiolysis. When we discussed all the oxidation states of americium, the autoreduction driven through the radioactive decay drives the reduction of species to the trivalent oxidation state. This is due to the formation of peroxide and radicals from the interaction of radiation with water in the solution. So the reduction rate has a difference for the different americium isotopes. This isotope effect is solely driven by the rate of decay and not the factor related to mass. So americium-241, with a shorter half-life than americium-243, should demonstrate more rapid reduction due to this radiolysis. Now the rate decreases with increased acid for perchloric and sulfuric systems, so there is some ability to limit or mitigate this radiation-induced reduction through the solution, there is some disagreement on the role of the americium concentration in the autoreduction. And it's unclear if it's the total americium or the specific oxidation state of the americium, which is the important consideration for the rate of reduction. However, it is known that the rate of reduction can be dependent upon the acid concentration, the mechanism. For instance, americium 6 going to americium 3 can go stepwise. Americium 5 tends to be slower than americium 6 reduction to the 3. This has to do with the fact that the 5 is slightly more stable. Another effect, which is similar to this autoreduction, is radiolysis. And this is just the formation of those radicals and variations in the chemistry due to the radiation. So not of the americium itself, but of the solution or ligands around the americium, and this can influence the americium speciation. So the radiolysis, for example, 1 milligram of americium-241 releases about 7 times 10 to the 14th electron volts per second, where bond energy is on the order of tens of electron volts. This is very much sufficient energy to induce reactions. Reduction of higher valent americium due to dose and electrolyte concentration was described above. However, there's other reactions that can occur. For instance, nitric acid can undergo reactions from the radiation to form nitrous acid. And in perchloric acid systems, numerous chloride species can be produced. Some of these chloride species can influence the redox behavior of metal ions, including the americium in solution, and the speciation, for instance, driving the formation of chlorides. Similar to other actinides, americium can undergo disproportionation. We discussed this with neptunium. For americium-4 in nitric acid and perchloric acid, there seems to be a second order with the americium-4 concentration, where 2 americium-4s disproportionate to the 3 and the 5. You can also get the americium-4 and the americium-5 disproportionating to americium-3 and americium-6. The americium-6 concentration seems to increase with sulfate. There's also the disproportionation of americium-5, similar to the neptunium system, where in 3 to 8 molar perchloric and HCl, reaction of 3 americiums with acid going to americium-3 plus 2 americium-6s plus water. The solution, so in other words, the acid solutions or the perchloric or nitric acid solution, is shown to impact the oxidation state stability for the americium and therefore has an influence on the disproportionation. The figures show the disproportionation of americium-5 and 5 molar perchloric acid and HCl. And you can see that the rates are different for the different acid systems. Americium can also be oxidized from the trivalent state. One widely used oxidation agent is peroxydisulfate. The figure shows the oxidation of americium-3. See that the amount of americium-3 decreases over time. The concentration of peroxydisulfate is constant. And what changes is the nitric acid concentration. And at lower nitric acid concentrations, the rate is faster, and at higher nitric acid concentrations, the rate is slower. We see that in a low acid concentration, 0.09 molar, labeled as A in the figure, the americium concentration is at about 10% of its total initial starting concentration within 2 hours. So this oxidation is due to thermal decomposition of the products, so sulfates and the hydrogen sulfates. The oxidation can go to americium-6. However, there is some acid limitations. Any higher acid concentration above 0.3 molar limits the oxidation. It's kind of shown in this figure where the high acid concentration is 0.28 molar. It's a much slower redox condition. There's an induction period followed by the reduction. So this really shows that the product, the peroxydisulfate, needs to get into a chemical form to provide the oxidation potential for the americium-3. The rates are dependent upon temperature and the compounds listed here, the peroxide disulfate, the nitric acid concentration. Sometimes the reactions are done with silver. In carbonate systems, this redox reaction proceeds through americium-5, so you go from americium-3 to 5 to 6, and the rate to americium-5 is proportional to the oxidant. And from the 5 to the 6 in the carbonate system, it's proportional to the total amount of americium and the oxidant, and it's inversely proportional to the concentration of the carbonate. So there's a lot of different trends that we can observe with the oxidation of americium-3, which actually means one can control and tune the oxidation of americium-3 to the desired americium final oxidation states. Americium-6 reduction can be performed with peroxides. In perchloric, it's first order for the peroxide and americium. The reaction is shown here, where you have two of the americium-6 oxidation states reacting with the peroxides. And reactions with neptunium-5 have also been observed, and it's first order with the americium-6 and the neptunium-5. So in this case, one would reduce the americium from the 6 to the 5 and oxidize the neptunium from the 5 to the 6. Oxalic acid reduces equimolar americium-3 and americium-5 from the americium-6. Americium-5 reduction, it occurs in sodium hydroxide solutions. There's a slow reduction with dithionite, sulfite, and thiourea dioxide. Neptunium-4 and Neptunium-5 can drive the reduction of americium-5 in both acidic and carbonate conditions. Americium-5 is reduced by Neptunium-4 with reaction products producing either Neptunium-5 or the Neptunium-6 conditions. And this depends upon the initial relative concentration of the americium and the neptunium. The reduction of americium-5 by uranium-4 has also been examined in carbonate systems. And we'll see in the Purex process that uranium-4 has also been used to reduce plutonium. So not only can you have auto reduction, but you can have, for americium, you can also have reduction by other actinides. Complexation chemistry of americium is primarily for the trivalent oxidation state. This is a hard metal acid, so the complexation of the fluorides, phosphates, thiocyanates, nitrates, chlorides, perchlorates are in the order common for harder metal ions. So this is primarily through electrostatic interactions in inner sphere and outer sphere complexation. Outer sphere complexation tends to occur for the weaker ligand systems. And the stabilities of the trivalent americium are similar to the trivalent lanthanides. There is a little bit of enhanced stability due to the 5f electrons that participate in the bonding of americium. And this is actually something that's exploited for separations of trivalent lanthanides from trivalent actinides. With this data, the table shows complexation constants for a number of different americium species that have been explored: americium hydroxides, carbonates, fluorides, solubility of oxides. So this means that the speciation of americium is fairly well studied for common ions, which provides a platform for understanding differences and similarities between americium and curium, and americium and the lanthanides. The thermodynamic data shown on the previous slide can be used to explore the speciation of some americium species. Here are some data calculated by CHEM for the hydrolysis of americium. It shows a very classic trivalent behavior. The figure on the top shows 1 millimole of americium-3. That around pH 6, the trivalent americium free species begins to decrease. The formation of mono, di, trihydroxide species increase, where the trihydroxide of americium dominates at the higher pH. The hydrolysis constants are available from CHEM, are provided here. You can compare those to the complexation constants on the previous slide. Carbonate species for americium is also well understood. Again, there's some 1 millimole of americium, 1 millimole of carbonate, showing where the americium hydroxycarbonate, so a mixed ligand species, dominates from around pH 5.5 to close to pH 8.5. Again, this changes the speciation, where particularly with this mixed hydroxide species, is an important consideration for understanding the full speciation of americium and the role of different ligands on a system. A number of americium organic complexes have been evaluated. General stability of the complex increases with the number of coordination sites. With amino polycarboxylic acid, complexation constants increase with the ligand coordination number. And there's also studies with natural organic acid, humic acids. A number of measurements have been conducted, been measured by spectroscopy and ion exchange. Natural organic matter is an important constituent in the environmental speciation of actinides, including americium. There's been some other specialized ligands shown here. Their general trend is that the stability of the complex increases with the available ligand coordination sites, as this figure shows. So both the beta 1 and the beta 2 for a number of different organic ligands are provided, and the trend holds fairly well. So this means if you wanted to prepare americium organic compounds with specific complexation constants, you can use this information to identify which species should have certain complexation constants based upon the coordination sites of the ligand. The fundamental chemistry that we just described on americium can be useful for separations. As we know, solvent extractions are useful separations techniques, with tributyl phosphate being a major workhorse in the nuclear fuel cycle. We know that in high acid concentrations, americium does not separate. However, in neutral or low acidic solutions with high nitrate, tributyl phosphate can be used to separate americium, extract americium into the organic phase. If americium is oxidized to the 6th state, you can get separations and extraction in 1 molar nitric acid. You can get good separations from neodymium due to the oxidation. And studies have shown using some polyoxymetalates, such as what's shown here, to stabilize the americium-6 so that it can be separated. There's other separations, dibutyl butyl phosphonate. It's similar functional group to tributyl phosphate, and it's shown to have a stronger extractant for americium than tributyl phosphate. Trialkyl phosphine oxides, as shown here, we increase the basicity of the P double bond O group from tributyl phosphate to the dibutyl butyl phosphonate to this molecule here, so that we can increase the extraction of americium. Americium and curium is extracted from 1 to 2 molar nitric acid with this ligand. And studies have shown with 30% TRPOs in kerosene, americium, curium, and the trivalent, tetravalent neptunium, plutonium, hexavalent uranium can be extracted. And these were done with C6 and C8 functional groups on the TRPO. Other solvent extractions that are used for americium includes HDEHP. This is part of the Tall-Speak process, which you can look at. You can look up in some links on the separations page, and will be part of the separations presentation. Tall-Speak uses HDEHP, nitric acid, DTPA, and lactic acid. So this organic, the HDEHP, is shown here. It goes into the organic phase. The DTPA, diethylene triamine pentacetic acid, remains in the aqueous phase, and lactic acid is used as a buffer. CMPO has also been used, the ligand shown here, and this is part of the Truex process, which is used for fission product extractions. So separation from the lanthanides and actinides from the fission products. And this, it also employs tributyl phosphate, the CMPO, oxalic acid, lactic acid, again as a buffer, and DTPA. Other extractants that have been evaluated include some amine salts. They've been evaluated in low acid, high nitrate, or chloride solutions. Common extractant is called this aliquot 336, which is shown here. This is useful for extracting in low acid and high salt solutions, and you get an extraction sequence of curium being less than californium, americium, and einsteinium. This has been examined at Argonne National Lab for process separations involving americium, the aliquot 336. There's also a number of amide extractants. The amide functional group is shown here. This is the basis of a process that's been evaluated in Europe called the Diamex process, where this malitamide has been used as part of the Diamex process, and in 3 to 4 molar nitric acids, now we're at higher acid concentrations, you get a selective extraction of americium over neodymium. Other separations have included separations of americium from the lanthanides with an extraction reaction. An example that's shown here is with Cyanex 301. This compound is shown here. This ligand is stable in acid, and as an example shown here, there's distributions of the trivalent americium and the trivalent lanthanides in 1 molar Cyanex. That's around 16 mole percent of Cyanex 301 in heptane. So you can use this ligand to achieve selective separations, and it's driven by the soft donor properties of these ligands. Irradiation studies have also been performed with phosphorus compounds, and extractions start to become problematic at relatively high doses. And this has led to the synthesis and characterization study of other phosphonic acids that tend to be less sensitive to acid concentration, less sensitive to radiation and hydrolysis effects. However, most of these ligands operate with synergistic extractions, so you tend to have more than one ligand in the solvent system. So, for example, these diphosphonic acids will work with tributyl phosphate, trioctyl phosphine oxide, or tributyl phosphine oxide. The aqueous phases are between 0.1 and 1 molar. So the acidity isn't as high as some of the extractants that we saw on the previous page, but they're in a regime which is relatively easy to control. Separation of americium and curium has been examined with ion exchange, and much of this exploits the fact that lithium chloride has shown to separate the actinides from the lanthanides. As shown here, here's an example of 10 molar lithium chloride separation. Distribution coefficients on Dowx resin, we see that the lanthanides have a very low distribution coefficients and the actinides a much higher distribution coefficient. So ion exchange has been used in 2 tracer type levels, one using a displacement complexing chromatography. It involves a 2 ligand system, 2 metals that act as competing cations. You use the slight differences in the complexation between americium and curium to achieve a separation. This method is somewhat cumbersome and complex, can be used on a small scale, but not particularly suitable to large-scale separations. Another route for separating americium, curium, and lanthanides is to sorb the material to a cation exchange resin at pH 2. And separation of curium from americium was achieved by using a relatively weak phosphonic acid solution, this ethylene diamine tetramethylphosphonic acid, at pH 3.4 in 0.1 molar sodium nitrate. And he achieved a separation factor of 1.4. Not a particularly high separation factor, but one that could be used to achieve a separation if enough effort is put into the system. Large-scale gram quantity separation of americium curium has been performed using cation and anion exchange, and it's using ligands such as alpha-hydroxy isobutyrate, which which we showed was used in the discovery of these elements to separate the lanthanides, and they also are useful in separating the actinides. DTPA can also be used as an organic ligand in this case, where the metal ions are sorbed to the resin and selectively removed with the acids. The LUN can be varied using a gradient of methanol and nitric acid. Best separations were achieved under high pressure. Separation factors can be as great as 400, much larger than the separation factor as we previously discussed. And the use of high pressure increases the theoretical plates of the system, enhancing the separation. Extraction chromatography is also performed with americium. One can think of extraction chromatography as combining solvent extraction and ion exchange, where there's a mobile liquid phase, generally the aqueous phase, and a stationary liquid phase, generally represented as the organic. So for the americium work, you can apply studies that were performed with the organic ligands such as HDEHP, CMPO, aliquot 336, and these are the basis of ichrome resins. There are some limitations in the solution depending upon what sort of ligands you have. These are mainly based upon the fact that these ligands will coordinate strongly with the metal ion, preventing interaction with the resin. There is another resin from ichrome which uses ethylhexylmethane diphosphonic acid on an inert support, and this extracts trivalent, tetravalent, and hexavalent actinides. In fact, this resin binds those metal ions so strongly that there's a need to remove the organics from the support in order to liberate the metal ions from the column. There's also variations of support. The ichrome resins are just hydrophobic interactions which keep the resins on the column. One can also covalently bond molecules to silica, and then some of these sites that it can be covalently bonded, you can coat the particles with ferromagnetic ferromagnetic properties. So after separation, you can use a magnetic field to separate the resins. You pull out the resins from the solution, thereby separating out any extracted americium. Other aqueous separation processes for americium include precipitation. This is driven by the formation of insoluble americium species, everywhere from trivalent to the pentavalent americium, here shown as the carbonate. Particularly this species, where americium can be oxidized to the +5, where curium cannot be oxidized, is a route for separating americium from curium. Americium can also be separated from the lanthanides by oxalate precipitation, where particularly the use of dimethyl oxalate as a route for this selective method of precipitation to achieve 50% lanthanide rejection, with only 4% americium rejection. So in this case, the precipitate winds up being enriched in the americium. Other routes for precipitation include americium-6 and the precipitation of curium-3. So in this route, the hexavalent state is soluble, where curium, as a trivalent, could be precipitated by such species as the fluoride. There's also pyrochemical processes for separating americium, particularly from plutonium, where if in a molten salt system oxygen is introduced, plutonium dioxide forms and precipitates. And americium can also be partitioned between liquid bismuth or aluminum and molten salts. I think this could be thought of as a solvent extraction system, where the solvents are molten salt and a liquid metal. Distribution coefficients of 2 for the aluminum system have been achieved for americium. Volatility-based separations of americium from plutonium can also be achieved by exploiting the the plutonium hexafluoride, which is volatile. So the formation of this fluoride species in a fluoride salt, so you start with the tetrafluoride of plutonium, bring it to the hexafluoride state, and achieve separation from americium by the volatilization of the plutonium species.
This concludes part 1 of the lecture on americium and curium. The nuclear properties, production of americium isotopes, and separation purification of americium was covered. When you've completed this lecture, please move on to part 2.